Okay, hello, greetings class. This is kind of going to be a test video, but I think it's also going to be a fun one. It's an important, it's less important, it's more so an interesting application of integrals and derivatives. It's important well, we're going to be talking about differential equations, specifically differential equations by separation of variables. And this is a important technique for, like things in which calculus is applied, like physics, engineering, stuff like that. Differential equations are very important for like applied mathematics, right? In calculus, it's useful to understand how differential equations, so like equations of derivatives, right, relate rates to like a function, right? So let's kind of put on our thinking caps here. Let's get right to it. As you can see, kind of changed things up a bit again. I got this kind of like wall sticking whiteboard here, which is cool. So I can just like write on the wall and no problem. I can just erase it. Cool. So we have a bit more space. I also have my usual board in case we need it. So differential equations. Generally, you're going to you're going to be given an equation in the form of, for example, dy dx is equal to, let's just say, x squared, right? X squared, right? This is a differential equation. Notice you're not given what y actually equals, but very often with differential equations, you are tasked to find what y equals, or find some sort of, like, if this is a rate, dy dx, a derivative, it gives you a rate of change, and kind of foreshadowing, we're going to use integrals to find not only y, the antiderivative of dy dx, but we're also going to be using y or dy dx in this differential equation method to find like numerical results for this, right? So let's kind of start actually with this example. I quite like it. We're going to start off with, okay, what is y? Our question is, what is y? How do we go about this? We're not given y. So this is where we're going to pull out a little trick. And believe me here, mathematicians hate this one trick. You heard it here, folks. We're going to take dx, we're going to move it over to the other side. We're essentially going to multiply dx by we're going to multiply both sides by dx, right? We're going to move the dx to the other side like this was a fraction, right? When dealing with infinitesimals and differentials, this is not really the case. And mathematically, you can really only do this if you're dealing with nice continuous functions. And that's one of the reasons why this is called separation of variables, because we take the variables and we just go whoop, and we're going to get dy is equal to x squared times dx, right? All I did was take dx and move it to the other side. Now, it's important here that your derivative is given in the form dy dx or dx dt, something like that, so that you can use this kind of like fraction manipulation, right? Now, if we recognize that the integral of dy is equal to y plus c, right, we can solve this differential equation. So this is where I'm going to pull out the other board, because I can't actually use my colored pens on the other board, right, or on this new board here. What we're going to do is we're going to take the equation dy equals x squared dx, and I claim we can just integrate both sides, such like this. Just integrating both sides. Oh, and I forgot the d. I just wrote x squared times x. Okay, cool. Nice. We can integrate both sides. The integral of dy is y. I guess technically plus c, we'll get more into that later. And then the integral of x squared is x cubed over 3. Also plus c. Now these are different plus c values. They don't have to be the same. So I'm going to go ahead and label them c1 and c2. But these are essentially just arbitrary numbers. They don't actually matter. So you can either, here, look at this. Y is equal to x cubed over 3 plus c. We only need one constant of integration. You can think of this in two ways. These c1 and c2 are totally arbitrary numbers. So you can kind of manipulate them and get another third arbitrary number, right? Or you can just do all the integration and then add the plus c at the very end. You can do that too. But look, we found an expression for y, only given a differential equation, dy dx, right? So with this knowledge, let's kind of tackle a more challenging example, more involved method, right? I'm gonna cook this up on the spot, so bear with me. We're gonna do this. Dy dx is equal to, I have a good one. X over y. Actually, no. That's not good. Y times x. Y times x. This is going to be an interesting one. Okay, so our step one, just like last time, we're going to move the dx over. This is equivalent to dy is equal to y x times infinitesimal dx. Okay, but we can't just simply integrate from here, because if we integrated both sides, I'll tell you why this is wrong. You have this y in the integrand, and you cannot have two changing variables, right? Like discrete variables or continuous variables in your integrand when you're only integrating with respect to one variable. Once you get to multivariable calculus or like vector calc 3, right? You can learn how to deal with this with like double integrals and far advanced techniques from what we're learning right now and more like introductory calculus. Long story short, we can't do this. We cannot integrate two continuous changing variables with respect to only one index, right? So we're gonna kind of backtrack here, and I'm gonna introduce you the next method. So just like we moved dx to the other side, we're gonna move y to the other side. And now the trick here, what I always like to remember, is get all of the like variables on one side. If you can do that, you can integrate smoothly. Here we have all of the y variables, including dy, on the left side, and we have all the x variables, including dx, on the right side. And now, same thing, I'm gonna, where did my blue marker go? I may have somehow misplaced my blue marker in the middle of the video. Oh well, I'll find that later. So we're gonna take this again. We're gonna do the same method. We're gonna integrate 1 over y dy and set that equal to the integral of x dx. Okay, cool. If you remember from, I forget how long ago it was at this point, a couple of videos ago, we talked about the integral of rational function. In this case, it's 1 over y. This is gonna be natural log of y. That logarithm base e, special kind of function there. And then on the right side, we have x squared. And I'm going to save the plus c's to the end because we still have more work to do. Because if we're finding y, we cannot simply just leave natural log of y as our final answer, right? And now I should note here before we continue on that, do you remember back to when we talked about implicit differentiation? This is not the same. We are fully allowed to integrate two separate variables with two separate integrals, given that we are, we have two separate infinitesimals here, right? We do not have to worry about any special like multiplying by dy dx with chain rule. We don't have to do any implicit differentiation stuff. We can integrate separately, and that's totally okay. Okay, now let's remember back to perhaps in a past math class, maybe like pre-calculus or algebra, you learned about what natural log really means. The way I like to think about it is, okay, if we have natural log of y is equal to x squared, well, the natural log is just log base e. So I always ask myself, okay, e to the what power is equal to y? E, which is like would be the base right here, to the this power over here is equal to your argument. Your argument here, which is what you're taking the natural log of, funny enough, is actually just like the answer of the natural logarithm. So I'm going to go ahead and rewrite this. And you can think of this as kind of like a loop. You go from like the base e to the right side of the equation to the argument, right? E to the x squared is equal to y. That's what we found out from this logarithmic equation. And we should add, I should rewrite this because it's the end of the problem, and I promised I would add plus c at the end. E to the x squared plus c. No, we can't. Okay, hang on. I messed up one thing. We actually do have to add the plus c over here. We have to add the plus c after we're done integrating, because now here we have an interesting one more trick. So that previous trick that I just showed you that I just erased would have worked if we were dealing with like bounded integrals, right? And then you'd plug stuff in at the end. But here, and use my mistake as a good example, whenever you integrate, whenever you are done integrating, before you do any other algebra or plugging in or anything, just add the plus c at the end. Don't forget the constant of integration, guys. Don't be like me. Instead, y is actually equal to e to the x squared plus c. And now we can remember, again, back to probably like pre-calc or algebra or something like that, that we can break up this exponential into 1 e to the x squared times e to the c, right? Because, you know, you can multiply two numbers with the same base. You can just simply add their exponents. Likewise, if you have a base with added multiple terms and it's a exponent here, we can split that up through multiplication. And now what we realize here, perhaps, is that e to the c is a constant number. And so this is kind of a very common like way you'll see differential equations written. This is actually a pretty common example, is this whole thing simplifies to, okay, y equals, often you'll see e to the c written as just some constant, usually like a, or like more commonly, I think, big capital C there. So I'm going to use capital C. Y is equal to c, e to the x squared. Because really c is some arbitrary number, and so uppercase C is e to an arbitrary number, so it's also just an arbitrary number, right? So this is our real final answer. Y is equal to c, arbitrary number, times e to the x squared, right? Cool. It's interesting now looking back on this how, you know, two linear variables multiplied by each other, x and y, you get this exponential business. And it's for this reason that, you know, or this is one of many reasons why Euler's number e is so important in common mathematics, because, you know, you would never expect like linear functions to turn into exponentials, but they do, and it's by this weird number. And it's because of this 1 over y thing. This that integral becomes natural log. Natural log has e in it. Okay, cool. We're gonna kind of take a more complicated example, but there's a clever trick to it, right? So I'm gonna start. And this is more on like, I think I'm probably gonna steal something directly from my current physics class. What we're gonna say is, let's have some new variables just for fun. dw dt is equal to f of x plus, actually, let's not be confusing here. Capital F plus capital G, right? And I'll label these like subscripts, just like mu and I guess like theta. Why not? These are just random functions that we don't really like. In reality, they're forces that I've labeled. Like if you're interested in physics, they're forces that I've just given names, right? But this is still a differential equation. Notice how our function is w, and our kind of bottom index here is dt. So I should say one thing. Neither of these have t. No, I'm not supposed to write on the board with colored markers here. It likes to stain the board. These functions have no t terms, right? And so what's interesting about this is, so like f of mu, for example, might equal like, oh, x squared plus y plus like z to the 20th, right? And like g of theta might equal like x cubed, right? But this doesn't really matter because we can solve out this differential equation same way. We can say dw is equal to, okay, f of mu plus g of theta, all of that times dt. And now, integrate both sides. We get all the way down here, w is equal to, that looks more like a Greek omega. W is equal to, all we have to do, since these functions don't have t in them, clever trick is we can just multiply the entire thing by t, because this is like we're integrating a constant with respect to t, right? We're going to get t times f of mu plus g of theta plus c. And that's really it. Okay. So now I want to use this exact same example to talk about bounded integrals, right? Now, all I'm going to change here is that we want the value of w from, say, 0 to 1, right? I shouldn't say that, actually. We're going to ignore that bound for now. We're going to say, this is kind of getting to more advanced, so I'm sorry. On the right side, because we're integrating with respect to t, we should have bounds that are with respect to t as well, right? Or in some way related to time. So I'm just going to say these bounds go from 0 to t. And this is a very, very common trick in calculus, physics, engineering, and all that stuff, where if you can't ever figure out your bounds, or you don't know what your bounds should be, 0 to x, or 0 to y, 0 to t, right? It's perfectly fine, because it's just a clever way to get out of having to do like plus c and initial condition calculations and all that. So I'm just going to say the bounds are from 0 to t for the purpose of teaching how bounded integrals work with differential equations. And on the right side, similarly, 0 to w, right? Now, we're going to solve out this integral again. We're going to get integral of 1 dw is equal to just w, but now we have bounded integrals, so we have to like actually worry about this. And I guess if you wanted to, you could call these all like dummy variables. If you remember when I talked about like dummy variables, I think I drew like a smiley face on these because technically they're different. Nobody really cares though. I don't care. Your teacher might care, your professor might care, your employer might care, whatever. I'm just gonna say they're the same thing. It doesn't really matter. And then this is equal to, again, same thing, t times f of mu plus g of theta, close bracket, from 0 to t. And I chose these bounds very specifically so that we wouldn't have to do much math. This is actually just going to be the same thing. We just get w is equal to t times f of mu plus g of theta. Right, okay. So this whole method of differential equations I showed you is called the method of separation of variables, right? Now, let's talk about, just for a couple minutes, about things we can't do. For example, if I give you dy dx is equal to x plus y, right now, and you won't learn this until very, very far down the line in college, probably, we can't solve this, right? These x plus y is not a separable equation, because if we were to use our normal method, we would get dy is equal to, okay, quantity x plus y dx, and we cannot integrate both sides because we have the extra y term over here. However, we can't simply just say that like dy dx minus y equals x. This gets really tough really fast because we can't physically separate y from x and keep our standard form of differential equation, right? We don't actually know how to deal with anything with our current methods involving like addition, subtraction, I believe exponents as well. Don't quote me on that though, because you might be able to do some goofy stuff. But really you're just looking at multiplication and division, nice well-behaved continuous functions on their domains. So anyways, with that, I hope you enjoyed this video about differential equations, kind of tying together a bunch of what we've learned so far about derivatives and integrals, because, you know, this is a derivative, these are integrals, this is an answer, right? yeah, separation of variables. Differential equations are nice and useful. They won't come up a whole ton. They're mainly a more like applied thing. If you keep on just going with math, you won't really see them a whole ton, but they're very, very useful in relating equations to their derivative, right? So anyways, thank you very much for joining me. Goodbye, class.